Mrs. John going through the Level 2 NCEA Physics, Electricity and Electromagnetic exam paper. So just make sure you have your resource sheet and that you use clear numerical working words or diagrams, and remember to include an SI unit with any problems. So here's question 1, which has to do with electric fields. So two parallel plates are set up 2.2 millimeters apart with a 15 volt between them. So what I did was I identified what is this 2.2? It's the distance, and that's your voltage. And there's one little tricky thing, it's in millimeters, so we need to convert that millimeters to meters. So the question is, show that the electric field strength between the plates is 6.8 times 10 to the power of 3 volts per meter. Now from your formula sheet, you'll see that the electric field strength has two formulae. One of them is E equals V over D. And the reason why we're using this formula is because we know the V and we know the D. Okay, so here's your voltage, here's your distance, which I've converted to meters now. So it's 2.2 times 10 to the power of negative 3. So there's your voltage divided by the distance. Always write an unrounded answer for show that question so that your marker will know you've actually worked through this. And here is how they want it. Now, an electron at rest is released from the negative plate and accelerates towards the positive plate. So if it's accelerating towards the positive plate, that means it's gaining kinetic energy and it's losing electrical potential energy. We have to calculate the maximum speed of the electron when it reaches the positive plate. So for this one, you need to look at your resource sheet because there's some information there. So the first thing is the electrical potential energy lost is kinetic energy gained. Electrical potential energy is the work done in moving that distance. Work is force multiplied by distance, and force is electric field strength times the charge, and here's the distance, so it's EQD, and that is equal to half mv squared, which is your kinetic energy. So if I rearrange this, just get v squared on one side, the half m goes to the other side, so the 2 goes on top and the m comes below. So that's why you get v squared is this. And then there's your 2, and I substituted for E, Q, and D. So the Q is charge on the electron, which is there in your resource sheet. It's divided by m. Now m is the mass of the electron. Why? Because the whole question is about an electron. And that also is given on your resource sheet. So when you do that, you get this number, and that was for v squared. So for v, you need to square root, and here's your answer. That's the unrounded answer, and then I just rounded it to 3 significant figures. Okay, next. A student states that increasing the distance between the plates while keeping the voltage the same will mean that an electron released from rest at the negative plate is accelerating over a longer distance and will therefore reach a higher speed than in part B when it reaches the positive plate. Use physics principles to explain why this is not true or why it's incorrect. Okay, so when I saw this, what's come to my mind is this equation. E is V over D, where E is the electric field strength. So if the voltage is the same, but you increase the distance, this ratio has to be the same. So that means your electric field strength will decrease. So I put that into words. So increasing the distance between the plates while keeping the voltage the same will decrease the electric field strength. Now since E equals V over D, now E is also equal to F over Q. So if that decreases, then the force on a charge or on electrons will decrease. Now voltage is the energy carried by charge, and the size of the voltage is the same, and the electrical potential and the size of the charge is the same. So these two are the same, so that cannot change. So the electrical potential energy lost will not change. Since EK is half mv squared and this is not affected by distance, the speed will stay the same because EP lost equals EK gained. Then state one thing that could be done to increase the maximum speed of the electron. So if the electron's got more energy, then it's going to reach greater speeds. How can it get more energy? By increasing the voltage. Then the next question is the diagram below shows the electrical field between a set of parallel plates d meters apart with V volts between them. So we've got letters, no numbers. Okay, the distance between the plates is now doubled. So the D becomes 2D and the voltage is half. So the V becomes half V. Okay, now state what happens to the strength of the electric field. So I got E equals V over D, but now the D has become twice and the voltage is halved. So E becomes V over 4 times D. So the electrical field strength will reduce to a quarter of its original value. Now using the same scale, draw in field lines on the diagram below to show the new electric field strength. So the electric field has now reduced by 4 times. So it's only a quarter. So I counted the number of lines here. There were 12. Okay. So a quarter of 12 is 3. There's already 2 lines, so I just needed one more in the middle. So that's how I got my single line. Okay, question 2, circuits. A student finds some car headlamps that are labeled 12 volts and 55 watts. So that's your voltage. Watts is a unit of power. So that's your power. Show that the resistance of a single headlamp is 2.62 ohms. So I did this in 2 steps. Power is voltage times current, or current is power over voltage, or current is, this is your power, this is your voltage, and you get 4.58 amps. And then I used V equals I times R because we're trying to find out R. So I know V and I now, and then you divide that and you get your R. Now the student connects 2 of these headlamps, so the resistance of each headlamp is 2.62. They're labeled A and B, and another lamp C, which is used to light up the number plate in the circuit below. The resistance of lamp C is 1.22 ohms. So what I did was I just put the values on my diagram, and then it says calculate the total resistance of the circuit. So this lamp C is in series with the battery or the power source, but these two are in parallel. So the way you get your total resistance, this is the one in series, but you know the resistance in parallel is that 1 over R1 plus 1 over R2, but that gives you 1 over R total. So just simplifying it, so I got 1 over each of these to the power of negative 1, and then this is the same thing, anything to the power of negative 1 is 1 over. And don't forget to do the negative 1 when these are in brackets. And you end up with 1.31. Then you add it to 1.22 and you get your answer. Okay, then what happens is the student connects a radio with resistance R to the circuit. So there's your radio connected to B. Okay, and the question is, use physics principles to describe the effect adding the radio would have on the brightness of lamp A. Assume the radio and lamps are all operating. Start by describing what effect adding the radio would have on the circuit resistance. So, what I did was, this is how I was thinking. So I just jotted down a few points. So when you add the radio has resistance. So the total resistance of the circuit is going to increase. If the total resistance of the circuit will increase, that hasn't changed. So the current drawn from the battery is going to decrease. So if there's less current going through C, then C is going to be less bright. Okay, but in this parallel branch, and there's less voltage drop here. So what happens in the parallel branch, there'll be a greater proportion of voltage, like that'll be less than before. So because the voltage across that and the voltage across this has to add up to 12. So if this one has decreased, the voltage across that's going to increase. So also when the current comes here to this junction, it's going to split into two, but it's not going to be an even split. The current always takes the path of least resistance. That branch has got more resistance. So what's going to happen is less current is going to go this way and a greater proportion of the current is going that way. So A is going to get brighter. So here's my answer. I'll read through. Adding a radio in series to B will increase the effective resistance of the circuit, thus lowering the current drawn from the battery. A smaller current through lamp C will mean that there is a smaller voltage drop across C. Now these are the nice physics terms, it's good to use. The source voltage is still 12 volts. So there will be a greater voltage across the components in parallel, that is the A, B and the radio. Since the current splits in a parallel branch, a larger proportion of the current will go through A as it has less resistance, that branch, compared to the B plus radio branch. Hence, lamp A will be brighter. It will have a greater power output due to greater voltage and current. Okay, then give at least 3 reasons why the circuit in part C would not be a good way to connect the 12-volt headlamps in a car. So since lamp C, sorry, that's my dog. Since lamp C is in series with the battery, if lamp C blows, neither of the headlights will work. Headlight A and B will be of different brightness. Since the radio is in series with the headlight B, the radio has to be on for the headlight to work. Okay, magnetic fields. So we've given the length of the wire, the magnetic field strength, and the width of the magnetic field. So that's as big as the magnetic field, but the wire is longer. Okay, now a wire is pushed through a magnetic field at a constant speed of 2.7 meters per second. Clearly mark the positive end of the wire in the diagram above. So I used my hand rule. Different teachers teach different rules, so you get the bottom as positive. So I use the left hand slap rule. You just go with whatever your teachers taught you and you get the right answer. Okay, calculate the voltage induced in the wire. So the formula is V equals BVL. So there's your B, there's your little v, which is the speed, and that's the length of the wire in the field. So this is tricky. There are 2 lengths. You always use the length of the field that you want. Okay, and you get that answer. The wire is now stationary and connected to a circuit that contains a 3.40 ohm resistor and a 12-volt battery. So now we're coming to the motor effect. Okay, so where there's a current and the current causes movement. Okay, so first thing, calculate the magnetic force on the wire. So F is BIL. Now the I is V over R. That's your V, that's your R. You get 3.53, and then you substitute for the B. The value for B is the same as here. This one, millitesla, you got to convert that to Tesla. So multiply by 10 to the power of negative 3. There's your current, and that's the length of the wire in the magnetic field, and you get your answer. And what's the direction? So if you use your hand rule, you'll see that it's going left. Okay, an electron cutting the magnetic field experiences a force that makes it follow a circular path. The electron is traveling from the left of the field, so I just drew an arrow, to show what's the left, so it's coming that way. Clearly mark on the diagram above the direction the electron moves around the circle. So I've just run my little thing. I used my right hand rule, but use whichever rule your teacher taught you, but that was for a positive charge, but electron is negative, so it has to be the opposite direction in which a positive charge will go, and explain why there's a force on the electron as it cuts the magnetic field. So as the electron enters the magnetic field, it will experience a magnetic force that acts at right angles to the direction of its motion, causing it to go in a circle. Now, the moving electron itself will have its own magnetic field. So now there's two magnetic field, the magnetic field around the electron itself and the magnetic field through which it is moving. So these two magnetic fields will interact, causing the field to be weaker on one side of the electron compared to the other, and that is why it moves in that path, circle. That's the end of the paper. Okay.